Okay, so the forces packet's on our Google Classroom forces unit, and we started from the beginning talking about our preconceptions, seeing what, if we remember what force was, what inertia was, maybe listing the forces we could remember, what friction was. Okay, and we started here on Aristotle to Galileo. Okay, so remember in the beginning, when we saw these natural motions of, for example, rocks falling, liquids flowing, flames going upward, we call these natural motions. Okay, then anything that needed a push or pull were violent motions. Okay, then we considered what happened when we dropped two pieces of paper. One was crumpled and one was flat. Now, when we drop them horizontally flat and crumpled, the crumpled ball hit the ground first. There was air resistance facing the horizontal paper. But when we eliminated air resistance and held it vertically, they fell at the same time. So we decided that the masses are the same, but they could fall at the same rate or different rates depending if there was air resistance. Also, what happened when you dropped two objects of roughly the same shape but very different masses? So even with different masses, they both hit the ground at approximately the same time. You would have to get very high for you to see a difference. Okay? Now, Aristotelian physics could not explain this, but they did say we can test this hypothesis that any two objects dropped from the same height will hit the ground at precisely the same time when using a vacuum. Okay, so this is Galileo's law of falling. And what we said was, Galileo's law of falling was, if air resistance is negligible, so negligible, then any two objects that are dropped together will fall together regardless of their masses, shapes, or materials. Okay, when we drew this, they gave us the example of a duck, a velociraptor, a notebook, a piece of chalk, even an individual atom will fall together. So we drew those. We drew the duck, the velociraptor, the notebook, the chalk, and an atom. We drew arrows of the same magnitude, and we wrote all fall together. Okay, and then also we talked about, for example, on the moon, a hammer and a feather were dropped together from the same height on the moon and fell at the same rate, hitting the moon's surface at the same time. So that was confirmed on the moon. Now, how do things move? We started with inertia, and we're transitioning into Newton's first law of motion. Okay, so what did we say inertia was yesterday? It's an object's tendency to keep on doing what it's doing. So guys, if an object is still, it's gonna stay still until something basically pushes or pulls on it to make it not still. If it's going, it wants to keep on going until something opposes it, which is mostly friction. So we usually, or they talked about inertia before they named Newton's first law of motion, also the law of inertia. So first off, inertia we said was an object's tendency to resist change, which means an object will want to keep moving or remain at rest. So an object's tendency to resist change, aka to keep moving or stay at rest. Okay, this is Newton's first law of motion, but we learn Newton's first law of motion in different ways. Okay, in elementary school and in middle school. So I would say in elementary and middle school, this is how we learn Newton's first law of motion. An object in motion
stays in motion.
And an object at rest
Stays at rest.
unless acted upon. Okay, so let's write that. So this is the first definition of Newton's law we learned. So an object in motion stays in motion, and an object at rest stays
Unbalanced force.
at rest. Unless acted upon. Good. I like how one of y'all said by an unbalanced force. That's now what we kind of talk about in high school. Now in high school, we summarize this and we say, we can summarize an object in motion stays in motion, an object at rest stays at rest by just saying an object will maintain its current state. If its current state's moving, then it's going to stay moving. If it's at rest, it's going to stay at rest. So an object will maintain its current state unless acted upon by an unbalanced force, and we'll talk about it what an unbalanced force is. Unless acted upon by an unbalanced force. And I'm underlining the word unbalanced because there's forces acted upon us all the time, but they could be balanced or they're just not great enough. So it really has to be an unbalanced force to throw us, quote unquote, off balance, to make us slow down or move if we're at rest. So both the law of inertia and Newton's first law are the same, to the point where they even call Newton's first law of motion the law of inertia. So an object wants to keep on doing what it's doing. An object's tendency to resist change, aka keep moving or stay at rest, an object will maintain its current state unless acted upon by an unbalanced force. Okay? So our first lab we're going to talk about, our first lab on Newton's laws, we'll talk about how Newton's laws are demonstrated and the objects want to keep on going, but something is slowing it down, aka friction. Okay? Okay. So, though this law is attributed to Sir Isaac Newton, it was actually René Descartes who invented this law. Consider an object in space, far from gravitational forces of other objects in space. If the object was stationary to begin with, then it will remain stationary. Oops, sorry. Until an external force acts upon it. Ms. Weiss, what's an external force? We'll learn about forces when we talk about free body diagrams in about a day or so. And there are forces intrinsic to objects, and then there's forces that act on objects that come, onto the object. Similarly, if the object was moving with a constant velocity, then it will continue at that constant velocity until an external force acts upon it. So continue at that constant velocity. Until an external force acts upon it. Okay, draw these situations to help remember Newton's first law, the law of inertia. So we're just going to draw a stationary object, draw an object with a constant velocity, and we're going to write them with our nomenclature. We haven't done that in a while. So I have an object, and this object is just still. Okay, and then I have an object I'll draw an arrow right now. That's like the whole, it's moving, okay? And so if an object is still, we want to draw its velocity. So we have v hat equals 0 meters per second. And just to review, remember v is speed, v hat is velocity. Velocity is a vector and needs 3 things: a magnitude, units, and direction. Why do we not include direction for this one? What is the only time we don't need direction on? So we have v hat
Starting point.
when it's 0. Okay, if you're telling somebody not to move, can you tell them a direction not to move in? No, but normally it will always need a direction. So when an object is moving at a constant velocity, now v hat, I'm just gonna make one up, equals 2 meters per second, bracket, north bracket. Okay, so now here's our vector quantity with magnitude, units, and direction. And remember, direction is always in brackets. I know we maybe did not use a lot of nomenclature last unit with our lab, our distance versus time, but we're gonna get back into using the nomenclature because we're talking about forces, which are vector quantities, okay? Okay, next thing you're gonna do, okay, last thing before y'all get to your practice. So, use Newton's first law to explain why it's important to wear your seatbelt in a moving vehicle. Okay, so I'm gonna try.
Do we have to draw this?
You don't. Okay, and I'm gonna draw a driver and a passenger. And I'm going to, in my green, because it's very good, having my driver wear their seatbelts. Okay, so use Newton's first law to explain why it's important to wear your seatbelt. So Newton's first law of motion states, inertia, an object's tendency to resist change. And Newton's first law is basically the same thing, but an object will maintain its current state unless acted upon by an unbalanced force. So ready? We have some kind of blockade, maybe a brick wall. Okay, this car is stopped. So use Newton's first law, aka an object wants to keep on doing what it's doing. We'll say that this car had a velocity of 60 meters per second northward. Okay? Both of these people, according to Newton's first law of motion, want to keep on going 60 meters per second northward. Okay, right? So according to Newton's first law of motion, and I'm not gonna write it, I'm gonna have y'all write it, but I'm just kind of setting you up for it. So according to Newton's first law of motion, an object wants to keep on doing what it's doing. Okay, so both people want to keep on going 60 meters per second northward, but one of them will and one of them won't based on the seatbelt. Okay, so y'all write this at your seat. This is going to be one thing I check when I collect the packet. Use Newton's first law to do that. Okay, everybody else, this is where the video is going to stop. Y'all have on the next page 4 practice questions. Okay, so it says practice, question 1, question 2, question 3, question 4. First one, some people believe that more massive objects fall faster than less massive objects. Describe a demonstration you could perform in your everyday life to clarify the concepts. Question number 2, define inertia in your own words, then rank the following objects from lowest to highest inertia. Plane, car, transport truck, basically a truck, motorcycle, toy car. Suppose you are being chased by a massive bull. Use the concept of inertia to explain why you could escape by running in a zigzag pattern. And number 4, use Newton's first law of motion to explain how headrests, so this is the back of the seat in your car, that help prevent whiplash in a motor vehicle accident. Well-labeled diagrams will aid in your explanation. Okay, so that is what we are finishing in class right now, and we will resume with Newton's second law when everybody turns this in. Y'all may rip that page out of your packet with your name on it and turn it in. So that is going to be graded the 4 questions.